All right. I am really excited to introduce Alexandre again. He spoke in my track last year and did a bang-up job. Last year was his first time speaking at any kind of big conference at all. Since then, he's gone on quite the world tour. He went to China, he went to Hack in the Box, he spoke in Europe, and now he's back here to speak again. Let's give Alexandre a big round of applause. Have a good time, my friend.
Thank you so much.
Yeah.
Hello, guys. Good afternoon. Let's talk about .NET malware reversing. It's a pretty easy talk. I think so. I'm a security researcher. Here is our agenda about my presentation. Here you have my last presentations on Confidence, DEFCON China, Hack in the Box Amsterdam, and DEFCON last year. I recommend you take some time to read it. In the last line, you see my tool, my personal triage tool, Malware View tool. If you have some free time, you can test it. And let's start. There are lots of people here. Honestly, once again, I was expecting 10 or 12 people because most malware analysts don't like .NET malwares. Basically, malware analysts, while analyzing .NET malwares, are concerned to unpack a binary from memory or find the encryption routine in a .NET malware, or even to decrypt resources embedded in this kind of malware. But according to my experience, .NET malwares can be so challenging because sometimes advanced authors, advanced malware authors try to modify the .NET malware, the application directly in the intermediate language, and I've been checking and analyzing some malwares in .NET which try to attack the .NET runtime. So it's recommended to learn a bit more on intermediate language and some information about the metadata in .NET runtime. Most of the time, we find .NET malwares around the world, and we have usually native code. A .NET managed code load native code on the memory. This is the common scenario, but sometimes things can be worse. Sometimes things can be a bit more complicated. You see, this is a real case that I faced some month ago. The suspect receive an email, click on the link, drop a first dropper. This dropper fetch a first payload on the internet. This payload is composed by two pieces. One piece is a native code. The other piece is an encrypted managed code. This first piece in native language, in native code, is injected into another process, in a remote process. Once this code is injected, this code loads the first managed code, the decrypt and load. This managed code fetch a second stage from the internet. The second stage is the real payload, and the infection starts. So things can be harder than usual case. And I try to showing in pictures here. I don't need to show you again how to make injection. Injection is so easy. I tried to show you here in this slide. This slide is a kind of refresh about injections. I won't explain it because it's pretty easy. But as I mentioned, things can be different. For example, I told you that usually I have a managed code loading a native code into the memory. But sometimes things are the inverse. I have a native code loading a managed code into the memory. In this case, for example, I use the CLR create instance to get an interface named ICLR meta host. From this interface, I use the get runtime to get another interface named ICLR runtime inf. From this interface, I use a new method named get interface to load the runtime. Afterwards, I use the execute application to activate the domain. I start the runtime using the start method. And finally, I use the executing the full application domain to start the real application, the real infection, the real payload. As you know, a .NET framework is composed by a runtime, CLR, and some libraries. Malware authors can write malwares using different languages such as C#, F#, VB.NET, and so on. Basically, these source codes are compiled into a common language infrastructure and finally run by the CLR. We have several excellent tools to analyze .NET malwares. I try to list some of them here. I use them daily in my daily job. Personally, I also use some additional tools that I try to show you here in red. These are great tools to analyze .NET malwares and reverse some of them. Of course, you must know that most .NET malwares use some kind of packers or cryptors. So I try to show you some of them here, and pay attention that the last one, VM Protect 3.40, was released, I believe, 1 or 2 weeks ago. And now it includes .NET obfuscation. When you are working with .NET malwares, you should or you must try to remember that most of them are using obfuscators, and obfuscators can obfuscating the control flow. This obfuscator try to rename methods, attributes, classes, and so on. Some of them encode all of the strings, of course. Try to encode and obfuscate the cross-reference. You know, it's so complicated to analyze this kind of code while you're using any kind of obfuscators. So it's very important that you know about that. When I'm analyzing a .NET malware, usually I see the same functions load the payload. In this case, I try to show it in green here. Assembly.load, assembly.load file, and method info.invoke is almost the same things. most time we see a kind of reflection approach. And when you see a reflection approach, you will see a sequence similar to that. I'm using load or load file, followed by get type, get method, and invoke the method. So reflections is so used during .NET malwares. So it's a very common approach. Another possible approach is using get assembly name plus get type, get method, invoke again. As most malwares have been using resources, or these .NET malwares try to hide some DL or payload into resources, you see sequences like this one in pink, find resource, size of resources, and so on. Sometimes you see other sequences like this one in orange, when malicious .NET assembly is trying to load some external DLL. All of these approaches are based on trying to load something in runtime to evade your static analysis. Here I'm showing you a first very basic malware. I open it in dnSpy. We have the entry point there in green. I click on the entry point. I find a class named the Pineapple Buffer Cache Event Source. Inside this class, I see the main function, and at the bottom, I see our potential malicious function named target invocation exception. Following this function, I see that this very special function is trying to load an assembly. And this function are using a URL to load this assembly, but in this case the web link comes from several attributes. For example, I took one, the first one, and I checked that this attribute is being set by getting a new assembly using get execute assembly here at bottom. This function is trying to read a resource. This resource is encrypted, and when you decrypt the resource, you see PE executable. So each of these variables are related to a resource that represent a possible or potential malicious native code. Here I'm showing the same code, but using intermediate language ASM. It's similar. You see the main function, the entry point. You see at right our function, our malicious function. We have a token. Token is that number 06. And this token works a kind of index inside a metadata table named member reference table there. And when I try to follow it, I find our function here at bottom, and more details are expanded. As you see, implementation flags are IL, intermediate language, and managed because I'm handling a managed code. This is a manifest. A manifest in this case is a file that wrap up everything. In this case, you can see the assembly name. You can see several managed resources related to embedded resources, and at the bottom you can see further information about this malware. As I mentioned before this point, this malware is using reflection to load malicious contents at runtime. So you can see here several calls to get execute assembly methods in several points in this intermediate language code. Sometimes you are facing bit harder .NET malware, and this malware brings some encrypted resources. So you can use dnSpy or other tool, drop this resource, decrypt it, and using Reflexo. Reflexo is a kind of plugin. You can add the original code and load the resource, the decrypted resource, to analyze the malware. In this case, you must remove the old references, because the old references are reference the decrypted resource. So in this case, you drop the resource, decrypt it, edit the original .NET malware, load it again, and that's it. You can analyze your .NET malware using this technique. Of course, it's always recommended to know a bit more intermediate language and, of course, metadata. I think that about 90% of cases, .NET malwares or .NET malware authors trying to insert some malicious code in or initializers or finalizers. In this case, for example, usually I try to check every class constructor to find or unpacker or decryptor or any kind of hooking code. It's very usual, for example, in the last few weeks, I've been seeing several .NET malwares trying to compromise the JIT. In this case, these special malwares, these special advanced malwares, trying to hook this function compile methods to compromise the JIT. In this case, when the JIT generates the native code, this special malware can hide or encrypt user code in runtime. For example, in this case, I try to see the class constructor. There, usually, I find some hooking code. This hooking code tries to compromise the compile method, and by using this trick, the malware can or hide or encrypt the user code. It's a very clever technique. There are other .NET details here. Most .NET malwares bring some very important metadata. So metadata basically are information about classes, attributes, members. Usually you get very valuable information from metadata. A .NET application, as you see, is composed by a managed executable and a managed code. It's not so hard to analyze this kind of code, but you need to have some guidelines to do that. For example, a managed code is composed by a P header, of course, CLR header, metadata, and intermediate language. In this case, I have the compiler here. I have the managed models. I have the resource files that are compiled to a final version composed by a manifest, a managed models, and a resource file. In using pictures, you see that a .NET header is composed by P header, CLR data, and native code. And at the right side, you can see the same picture, but in a detailed view. Metadata is very important because there I can find very valuable things and information. Metadata in this case is composed by definition tables, reference tables, and manifest table. There are several tables inside of these classes. And you should remember that all the .NET malware infection try to use one of these tricks, or code manipulation inside the class constructor or finalizer, try to load some managing function, or use a component. So the tricks are the same, always the same. Here is a second case, a bit more complicated case. This is a real .NET malware. I'm showing here the intermediate language and the metadata information. As you see the name, type def reference table. You see the method name, in this case man, and the flags. In this case, I'm using the IODES to show this screen. As you see, the real managed code is so small, less than 5%. Metadata is so important because, as I told you, it describes some information about members, attributes, properties, classes, and so on. This metadata is organized by using a kind of relational database. And it's so interesting because you see I have a table, 1, 2, 3, 4, 5 slots. Each slot is dedicated to a class, and each slot tells me which methods belong to this class at right. These metadata are organized in named strings and classified in metadata heaps and metadata tables. Metadata heaps is so easy because there our only concern is about strings. So a string heap is more important for us. And inside these 6 named streams, we have hash US is related to user strings, and hash dash is a kind of uncompressed metadata stream. So I believe that these 2 ones are the most important. When I talk about metadata table, we have several tables. It is almost impossible to remember every table. You see, I list all the tables here, and since here works using a token. A token is a kind of structure composed by 4 bytes. The first byte determines the table. The remaining 3 bytes tell us the row inside this table. Here I show you some statistical information about metadata. And at bottom, I show some user strings that I commented about the named strings. Intermediate language in .NET is a kind of ASME language based on stacks. So you see several instructions. Load something onto a stack or pop something from stack. You see a very usual application or tool named Engine. Engine is a executable to compile intermediate language code into a native code. It's so easy to do that. But in the last 3 years, I've seen several malwares trying to attack the .NET framework. In this case, this kind of infection are a bit more complicated. We have several kinds of .NET malwares, but assemblies are classified in private assemblies and shared assemblies, of course. You should remember that most malware samples try to hide some malicious content in resources, hide by encrypting or obfuscate something. Some .NET malwares try to download an external assembly from somewhere, and other .NET malwares are based on multi-file assemblies. In this case, it's a bit more complicated because these authors try to compose the .NET assembly and split over multiple files to evade the defenses. It's so easy to generate a multi-file .NET malware. For example, I show you here a step-by-step. In this case, it's so easy. I compile, for example, a hooking.cs model. I compile a injection.cs. And using a main program named defcon.cs, I generate a library named malwarelib here. It's so easy to do that. Of course, this operation touches several metadata tables, but it's normal. Here, we have a real manifest about our second malware. You see some native models being loaded at bottom, some external reference to assemblies, and in this case, our assembly is a strong assembly because it is digital. It's signed by a private key from somewhere. The second screen here, you see the driver, the assembly name. You see several custom attributes. You see that the signature is using SAJ1 algorithm. You see several managed resources being used. And at the bottom, you see that the real name of this malware is microtik realtek driver.z. I show you here how to compile a final executable in C#. It's pretty easy. If you have a key pair, you can sign disassembly by using this procedure here at the bottom. After signing this .NET assembly, you can see the public key there in red. During some infections, I've seen native codes trying to copy .NET assembly to GAC. GAC is global, means global assembly cache. In this case, the author was trying to execute the native code, copy the managed code to GAC, because other pieces of this malware would use this shared assembly in the GAC to continue the infection. It's a kind of second stage. It's pretty easy to copy to that because you can use GAC util there in orange, or you can use the MSIL package to do that. Of course, to copy anything to GAC, you need to have a key pair to sign your .NET assembly. If you don't have one, you can use only the public key and trying to delay signing. In this case, you will sign the .NET assembly, only use the public key. To do that, you can follow this procedure. You can add some resources by using /resource. You can add some references by using /references. It's pretty easy. Of course, I don't have enough time here to show you how to explain every single instruction in intermediate language. So I left some slides here showing each important instruction in intermediate language. I don't have enough time to do that, unfortunately. And here I show you a real malware. Is the same malware. So I try to comment several lines. Of course, you must know about C# to understand this code. Here, we don't have anything different from a C# code, but the names and the keywords are a bit different. You have a public class, you have a private class, you have a sealed class, you have a constructor here, a CTOR, you have some private fields, we have some stack reservation there, max stack. You have several operations, load things to stack and pop things from stack. You have a custom instance here at bottom. You have private class. You have invocation of a native code in the middle here. You see pinvoke implementation here, trying to call a managed code. You have here at bottom local variable being initialized with zeros. We have a try-catch structure, so it's so similar to a C# code. I try to comment several lines here to help you later. You have, for example, here, our .NET malware are interested in get or keystrokes. You see, in this case, malware is trying to hook some keyboard operations. As you see, the .NET malware is trying to hook the key down event and key up event. So it's a kind of keylogger. At the bottom here, we have some event declaration. In this case, our .NET malware is trying to subscribe some functions on this event. At bottom, key down. At up, key up. And finally, our .NET malware using aggregate to invoke this event. So easy to do that. Several constructors being called here. Oh, finally, I found the decryption function. This function is responsible for decrypting several strings from this malware. As you see, I try to comment line by line, or the most important line here. You can try to monitor all DLLs load from the GAC by using fuzzlog or even process monitor. But as I told you, some advanced malwares try to compromise the .NET framework, try to insert some hookings, and even trying to compromise the JIT. So it's this kind of malware are more dangerous. Here at bottom, I show you the complete procedure. For example, I can copy a DLL from GAC, modify, recompile to the native code, and copy back again to the GAC. It's so easy, pretty easy to do that. Of course, nothing is so simple to do that. I needed to have a signed assembly, and as I don't have the private key from the Microsoft, it's so complicated to do that. Other approach, it would be to resign all the .NET framework. It's so hard to do that. I can try to copy the modified DLL to GAC, but if some applications or services are using this DLL, it's not possible. I can try to force a reboot to make this copy. And even that I get it to do that, I need to force my current applications using this modified DLL. So in this case, I need to uninstall and remove the native code from the native directory. K-Smith show a very interesting way to do that. K-Smith show a very nice trick by dropping assembly to this path tasks .dll to force applications using my modified DLL. I can try to, for example, I have a register composed by two entries. One entry is pointed to the assembly code. The other entry is pointed to the native code. In this case, I try to change the second entry to point to my modified DLL. Is another approach here. Some .NET malwares try to compromise services, try to introduce some hooking in JIT. Some .NET DLL try to load external assemblies. So there are several tricks. Of course, I've been using WinDbg to analyze this kind of .NET malwares using an extension like SLSX. And here, I show you a complete approach. For example, here I load the extension SOS.dll. I found the native entry point, the managed entry point. I disassembled the entry point. I found the PE entry point there by using dump bin. I try to display the pointer, and finally I find the core easyman function by disassembly. I can dump the domain. In this case, I see the system domain, I see the shared domain, I see our domain that from our malware. I see several calls to external assemblies, Visual Basic, setting the DLLs, forms, and so on. I list some managed exception. I can try to switch the thread, for example. In this case, I switched to thread 0. I dumped the managed stack trace here. I found our .NET malware at bottom. I list some managed threads by using bank threads here. As you see, you can see that threads 0, 2, 5, 10, and 14 are managed threads. All of them are managed by garbage collector. I list the native stack at bottom using key N. I pick up an entry there. I check that if this address belongs to the JIT code, yes, in this case belongs. I pick up the method descriptor reference. I disassemble it, so we have the disassembly function here. I check the managed stack again. I pick up object address. I check it again if this address belongs to the JIT. Yes, again. I dump the method descriptor information here. I pick up the class reference at top. I dump the EE class structure information. I found that this specific class has 6 methods, 28 instance fields, and 5 static fields. I can check one of these fields, for example, in this case a value type field, by using dumpvc. I found a hash table class composed by several fields here at right. I dumped the math table information. I dumped the math table information again, but detailed output. As you see, several methods, some of them pre-edited, pre-compiled. I dumped information about a specific model. I found the assembly reference. I dumped the assembly information. I found the parent domain information. I dumped the domain information at bottom. It's pretty easy to do that. Of course, here is a bit more complicated. Finally, I start again. I found the method table structure and E structure here. I found some interesting classes, possible malicious classes. I take one, testprint.client. I dump some information from this class. As you see, there are several methods there. I pick up one. I dump the class, and it's very interesting because there I found some fields in English, Portuguese, and German language. I took the German one to check the information. As you see, this part wasn't executed by JIT because at bottom is JIT no. So I tried to put a breakpoint to a future execution. I dumped again all of the stack objects. I saw a function using a an array. I dumped this array. This array is composed by one element that in this case is a structure, as you see at bottom. I dumped, okay, that's the same slide. I checked the heap information. I check any kind of references to these objects by using gcroot. References from the stack and from the handle tables. I check the finalized queue to find something interesting. I check the pinned handles because some malwares cause strong heap fragmentation. I check again some problems with locks and deadlocks. I try to find a string inside the heap, the managed heap. At bottom, I dump the malware from memory. And finally, I check the thread environment block. I dumped some strings from there. I found some nice strings at bottom. I dumped all of the heap. I found some classes. I took one keyboard hook, and so nice. I dumped methods from these classes. There are several methods. I took the last one, tried to disassemble it in intermediate language, try to dump all strings from the memory related to this method. And it's nice. I found several URLs related to banks. So this is a kind of Trojan banker. I'm leaving some breakpoints for you here. These are very nice breakpoints to test, to gather some additional information. And I test. The URL in VirusTotal by using malware view. I can see that is a malicious site. And I test the domain, and I found several related things, several malicious things associated to this domain. It was a very long presentation. I know about that. If you want, I can expand details for you. Thank you so much to the DEFCON staff, as usual, for you who reserved some time, and have a nice day. Thank you.
Wonderful job. Wonderful.